Deep in the heart of southern China, where the Guangdong coastline meets the open water of the South China Sea, a stretch of ocean 108 kilometers wide separates the Chinese mainland from the island of Hainan. The seabed here drops over 100 meters in places. Strong currents run through the strait year-round. 400 vessels cross the surface every single day. For decades, the only way across was by ferry, a crossing that took 90 minutes in good weather and shut down completely during typhoon season for weeks at a time. Engineers had one objective: bore a tunnel under all of it from one shore to the other without building a single visible structure above the water. The project ran for 7 years. No cranes on the surface, no construction platforms rising from the sea, no activity visible from a passing ship. And when the announcement came, the tunnel was already finished. This is the Chongzhou Strait Submarine Rail Tunnel. Before a single machine entered the ground, 12 survey vessels spent 14 months crossing the strait in overlapping grid patterns, mapping every layer of rock and sediment below the seabed down to 300 meters. Sonar pulses fired every 10 seconds from equipment towed behind each vessel. Drill ships anchored at over 200 points along the planned route and pulled core samples directly from the ocean floor, each sample 3 to 9 meters long, extracted from up to 80 meters below the seabed. Every sample was shipped to a laboratory in Guangzhou, cataloged and analyzed. The geological picture that emerged showed alternating layers of soft sediment, basalt, and fractured limestone, with 4 fault lines crossing the planned route at different angles. The engineers knew exactly what the machines would face, kilometer by kilometer, before the first meter was dug. In March 2018, construction shafts opened simultaneously on both shores, one at Zhuan on the mainland, one at Haikou on the island. The clock started on both sides at the same time. Each shaft was 32 meters wide and 60 meters deep, sunk straight down through urban ground. The method used was a second pile wall, where interlocking concrete piles were drilled in a ring around the full perimeter before any internal excavation began. The piles were each 1 meter in diameter and went 75 meters into the ground, overlapping each other to form a continuous watertight wall. Only then did excavators begin removing earth from inside, working 1 meter at a time from platforms hanging from a gantry crane at the surface. Steel ring beams were bolted against the inside of the pile wall at every level to prevent the ground from pushing inward. At 30 meters down, groundwater began forcing through the joints between piles. Grouting crews sealed each inflow immediately, injecting pressurized cement into every crack until the water stopped. Both shafts reached their final depth of 60 meters in late 2019, 15 months after drilling began. At the base of each shaft, construction teams assembled the full supply infrastructure needed to feed tunnel boring machines operating 50 or more kilometers away underground, concrete segment conveyors, slurry feed and return pipelines, ventilation ducts, power cables, and data lines. Equipment moved up and down those shafts around the clock from the first day of operation. 4 tunnel boring machines were lowered into the shafts in sections and assembled underground over 4 months each. Each completed machine was 114 meters long from the cutting face to the end of the trailing gantries behind it. The cutting wheel at the front was 15 meters in diameter, ringed with 240 steel disc cutters set in a spiral pattern across the face. These machines used pressurized liquid at the cutting face to hold back the enormous weight of water and earth pressing in from outside the tunnel. Without that pressure, the ground at the face would collapse in seconds at these depths. The liquid absorbed the broken rock and soil as the wheel cut through and carried everything back to the surface through a pipeline running the full tunnel length. Separation plants on the surface ran continuously, pulling the rock particles out of the liquid and pumping the cleaned mixture back down to the face in a closed loop. 2 machines launched from Zhuan heading south under the strait. 2 launched from Haikou heading north. All 4 drove toward each other through solid rock under 100 meters of ocean, with no contact with the surface above them. The cutting wheels turned continuously at 3 revolutions per minute. In good ground, the machines advanced 10 to 14 meters every day. Behind the cutting shield, a ring-building robot installed the tunnel lining in real time as the machine moved forward. The lining segments were pre-cast concrete panels manufactured at a casting yard 8 kilometers from the Zhuan shaft. Each complete ring was made from 9 curved segments bolted together, each segment weighing between 6 and 8 tons. A complete ring was installed every 22 minutes. Immediately after each ring was built, grout was injected through ports in the segments to fill the gap between the outside of the lining and the surrounding rock, locking the structure in place and transferring the ground load directly onto the concrete. The whole sequence, cutting, ring building, grouting, moved forward as a single continuous operation without stopping. Segment delivery trains ran a continuous circuit from the bottom of the supply shaft to the ring building position, loaded going in and carrying spoil containers coming back out. At peak production, over 300 tons of concrete segments moved into the tunnel every single day just to keep the machines supplied. Workers operating the cutting equipment worked in conditions of elevated air pressure, because the system at the face had to maintain higher pressure than the groundwater surrounding the tunnel to prevent water from pushing in. Passing between the pressurized zone and the normal pressure zone behind required moving through an airlock chamber and spending 40 minutes equalizing before continuing. A team of 20 workers ran each machine per shift, watching screens that showed face pressure, slurry flow rate, cutting wheel torque, advance rate, and lining grout pressures simultaneously. A drop in face pressure triggered an immediate alarm and a manual check of the supply line. In the ground conditions under the straight, a pressure failure at the face would allow water to enter the cutting chamber within seconds. Every alarm was treated as real until it was confirmed otherwise. No alarm was ever ignored. As the machines descended below the coastline and moved into open water territory, the depth of the tunnel below the seabed increased progressively until the crown of the tunnel sat 65 meters below the ocean floor at the deepest section. At that depth, with over 100 meters of water above the seabed on top, the pressure on the outside of the tunnel lining was equivalent to the weight of a fully loaded freight train pressing down on every single square meter of the concrete wall. The lining segments manufactured for this section were built to a heavier specification, with additional steel reinforcement and greater thickness, to carry that load without cracking. Grout injection pressures were increased to ensure every void behind the lining was completely filled. The machines moved slightly slower through this section, not because the ground was harder, but because every ring required more checks and more time to confirm it met the tighter quality standard before the machine advanced past it. Midway through the undersea section, at the point where both sets of machines were deepest below the seabed and furthest from their respective shafts, the logistics chain keeping them supplied stretched to over 50 kilometers in each direction. A segment delivery train leaving the Zuen shaft took 40 minutes to reach the cutting face. The train carried 12 segments per run, enough for 1 1/3 rings, to maintain a ring installation rate of 1 ring every 22 minutes. Trains had to depart the shaft at intervals of under 30 minutes around the clock without interruption. A delay anywhere in the chain, a mechanical fault on a train, a blocked section of track, a slow grout injection on a previous ring, cascaded immediately into a slowdown at the face. Logistics controllers monitored the position of every train in the tunnel network from a surface control room and rerouted or accelerated trains in real time to prevent any gap in supply reaching the cutting team. At no point during the undersea section did a supply interruption cause the cutting wheel to stop turning for longer than 45 minutes. The deepest section of the route also brought the coldest working temperatures inside the tunnel, as the rock surrounding the machine was consistently colder than the sections closer to the mainland. Condensation formed on the tunnel walls and equipment surfaces. Electrical insulation on cables and sensors required weekly inspection to check for moisture penetration. Lighting levels in the working area behind the cutting shield were increased to compensate for the reduced visibility from water vapor in the air. Workers in this section wore additional waterproof layers under their hard hats and high visibility vests. The machines themselves showed no reduction in performance. The slurry system that kept the face stable was designed for conditions far more challenging than cold, wet rock, and it operated within normal parameters throughout the deep water crossing. At kilometer 82 from the Zuen shaft, the lead machine entered a zone of heavily broken basalt sitting directly on one of the 4 fault lines that had been identified in the original seabed survey. Water began forcing through cracks in the rock at the face at a rate the pressure system could not fully control. Advance stopped. Probe drill rods were pushed forward through ports in the cutting wheel, sampling the ground ahead and measuring water pressure in the fractures. The readings confirmed the fractured zone extended at least 200 meters further along the route, and that the water pressure inside the cracks was high enough to force water through the tunnel lining itself, if the ground was not treated before the machine cut through it. Grouting crews moved to the face and spent 51 days drilling holes outward in a fan pattern around the full perimeter of the planned tunnel profile ahead, then injecting cement under high pressure into every fracture the drills could reach. 480 holes, 15 meters each. When follow-up probe drilling showed the water inflow rate had dropped to safe levels, the cutting wheel started turning again. The fracture zone took 28 days to pass through at reduced advance rate. The finished lining rings in that section showed no cracking and no water seepage. By February 2025, all 4 machines had completed their drives. The 2 machines cutting north from Zuen broke through into reception chambers on Hainan on consecutive days in February and March. The 2 machines cutting south from Haikou completed their drives 4 months later. Each breakthrough was controlled precisely. As the cutting wheel approached the final wall of the reception chamber, the advance rate dropped to 2 meters per day, and the face pressure was managed carefully to prevent ground movement at the point of breakthrough. The instant the wheel broke through, workers waiting inside the chamber behind a steel protective barrier moved in to seal the gap between the machine and the chamber wall. The machines were then disassembled underground. The cutting wheels were cut into 12 sections each using gas-cutting torches before the pieces were small enough to lift up the shaft. Full retrieval of each machine took 11 weeks. With all 4 drives complete, fit-out teams moved through the tunnel system installing the track, overhead power supply, ventilation, drainage, lighting, communications, and fire detection equipment that turns 4 concrete bores into an operational railway. The track was laid as a concrete slab system, with the rails mounted directly on a continuous concrete base cast on the tunnel floor. Rail teams worked from both ends simultaneously, moving toward the center. Overhead, catenary wire was strung from brackets fixed to the tunnel wall at regular intervals along the full length of both tubes. Ventilation fans at each portal were capable of moving enough air through the tunnel to clear smoke from a fire in the tunnel to a breathable level within 8 minutes. Every system was tested individually first, and then as part of a fully integrated test before trial running began. Cross passages connecting the 2 main tubes were cut through the rock at 500-meter intervals along the full length, creating 212 connecting corridors between the tunnels for emergency evacuation and maintenance access. Each cross passage was excavated by hand using steel arch frames and sprayed concrete, a process that took 18 days per passage on average. Up to 40 cross passage excavation teams worked simultaneously in different locations along the tunnel while the main tube fit-out continued around them. On September 18, 2025, the first train ran the full length of the tunnel. A 16-car high-speed train entered the mainland portal at 250 kilometers per hour and emerged at the island portal on Hainan 26 minutes later. Engineers watching instrument screens along the full route recorded rail vibration, tunnel air pressure, overhead wire voltage, and lining movement readings at every kilometer. Every reading was within the acceptance range. The train made 3 return runs that day. Revenue service began 6 days later. The first morning departure from the mainland carried 340 passengers. The crossing took 31 minutes door to door. The fastest ferry it replaced had taken 1 hour and 25 minutes in calm conditions and did not operate at all during typhoon season for an average of 37 days per year. The tunnel runs in all weather every day. In the first 3 months of operation, the tunnel carried over 9 million passengers. Freight trains began using the route in October 2025, moving cargo that previously had to be loaded onto ferries, carried across the water, and unloaded on the other side, a process that took over 3 hours from terminal to terminal. The tunnel reduced that to under 40 minutes. Hainan had received the majority of its mainland supplies by sea since the island was first settled. For the first time, it had a permanent land connection to the national rail freight network, operating in any weather, at any time of day, every day of the year. A southern extension from Haikou to Sanya is in the planning approval process, with construction projected to begin in 2027. If you want to see more projects like this one broken down from start to finish, subscribe so you do not miss the next video, and drop a comment right now telling us where in the world you're watching from.